Okay, here we go. Lesson 6.3, exponential functions. So what are you going to learn? You're going to be able to identify and evaluate exponential functions and then graph them. All right, so we have a little bit to talk about here. So when we have an exponential function, we're talking about a function that is nonlinear. And here's the form. Y is equal to a times b to the x exponent. A cannot be equal to 0, right? Because 0 times anything is just 0, so that would be a line or a linear function again. B cannot be equal to 1. Remember, if B were 1 and you change the exponent, 1 to the power of anything is always 1. So then that would just be 1 times this value, which is a constant. So therefore, it would again be a linear function. And B must be greater than 0. So we're only going to be talking about like positive values, right? So it can be a fraction. It can be between 0 and 1, and it can be greater than 1, but it cannot be equal to 1. Okay. So as the independent variable x changes, the dependent is multiplied by a constant factor. So let's just say we had y is equal to, and I'll just do like a parent function, right, without an a value, or a equal to 1. Say 2 to the x value. So this is what an exponential function looks like, meaning that every time, right, you make a table and you say you have, you can have x equal to 0, 1, 2. You can have x equal to negative numbers as well. But let's look what this does to this, right? So then we would have, and this would, I'll substitute this in, we'd have 2 to the 0 power. Well, that would be equal to 1. Okay, here we have 2 to the first power, so that's equal to just simply 2. Here's 2 squared, so that's 2 times 2. This is 2 cubed, right? I'm substituting the 3 in for the exponent of x right here. So that would be equal to 2 times 2 times 2. So what we've done as we've, followed this pattern and looked at the output values is we're multiplying by a factor of 2 every time, okay? So that's something that we're going to be learning about today. All right. So to be able to identify the function, we want to know if it's going to be linear or exponential. Remember, linear has a common difference. Okay, and what we just kind of looked at is that this exponential function has a common ratio. So instead of adding something every time or subtracting something, we are multiplying. So we have, let's see, we have, examining this, this is going up by 1. And so this is going up by 2. And it's kind of following that pattern, right? So we can see that as x increases by 1, y increases by 2, the rate of change is constant and it's linear. Here, if we were to try to say, okay, this is going up by 4, but this is going up by 8, notice that by adding, it's not a constant rate. Therefore, you need to look further to see what the pattern is, 4 times what equals 8? Well, it's times 2. 8 times 2 is 16, and 16 times 2 is 32. You can also find this by taking 8 divided by 4 is equal to 16 divided by 8, which is equal to 32 divided by 16. So we're looking for that common ratio, and you can look at it, find it that way as well. Okay. So let's give some of these a try. So let's go ahead and determine whether this represents a linear or exponential function. So we're looking for, we want to know if we have a common ratio or a common, so we always look at the x, and we can see this is going up by 1, so that's good. Here, all right, subtract 4, subtract 2, subtract 1. Therefore, it must be some kind of a ratio. Well, how do we get from 8 to 4? We divide by 2 or we multiply by 1/2, right? So if we wanted to write this, like I said, as a ratio, 4 divided by 8 has to be equal to 2 divided by 4 has to be equal to 1 divided by 2. All right, so you're going to compare it that way. So 1/2 is our common ratio. And if we have a common ratio, then it is exponential. It's an exponential function. And we'll explain it that the common ratio is 1/2. Okay. Number 2, again, we check this is going up by 1. Great. So this is going up by 4. I always like to try my common difference first. Look at this. We have a common difference. Since we have a common difference, that makes it linear. There's a constant rate of change. As x is increasing by 1, y is increasing by 4. On number 1, we could say as x is increasing by 1, y is increasing by a factor of 1/2. And maybe instead of saying is increasing by 1/2, because we can obviously see that this number is decreasing, maybe say that it is being multiplied by 1/2. That's probably a better way. So we have a common difference here of plus 4. Okay. Okay, so why don't you go ahead and pause the video, and I want you to try number 3, and then I'll keep working ahead and I'll do number 4. So I'm going to first look to see if there's a common difference. So I would try 0.5 minus 0.125, and I get 0.375. But then I know when I take 2 minus 1/2, that's not going to be the same. So there's no common difference. So then I'll take 0.5 and I'll divide by 0.125, right? Because I want to take the common ratio of, and I'm just going to use the decimals, even though we know we don't necessarily leave decimals in ratios. Then we'll take 2 divided by 0.5, and then we'll take, that has to be equal to 8 divided by 2. Well, obviously this one's the easiest one to do. So we just check these to make sure that they are all equal to 4, and they are. And so what's happening is it's increasing, and it's increasing by a factor of 4 each time. And of course we have also double checked, oops, I think that's supposed to be here. There we go. There's only 3. We also double check that this is increasing by 1, and it is. So x is increasing by 1, y is increasing, being multiplied by a factor of 4. And it's probably better to say being multiplied by, because like we noticed, some of these are increasing, some of these are decreasing, all right? And that's going to be for another lesson in this chapter. So that makes this an exponential function. All right, and we have a common ratio. So as it's 4, common ratio of 4 being multiplied by 4. So as x is increasing by 1, y is being multiplied by 4. All right, so to evaluate them, this is where we get to use our calculators. So this is, this is in the form y is equal to a times b to the x. So b, which is our common ratio, a, we're going to learn about, is going to be our y-intercept, because we said that if x is 0, this whole term, 5 to the 0, becomes 1, and then, negative 2 times 1 is negative 2. So this is always going to be known to us as our y-intercept in these types of graphs, because we will be graphing them today. So you will be substituting in the x for the exponent and then evaluating. And remember that b is the only thing being raised to the exponent of 3. So as we've learned our exponent rules this chapter, 5 is the only thing in this case that's being raised to the exponent of 3, which is 125 times the negative 2. And so that would be the output value of y. Here, we said we could have this as a decimal or a fraction, so 1/2. You have 1/2 raised to the x is equal to negative 2. Now think about that. What does that mean? So 1/2 to the negative 2 is kind of like saying we're going to take 3 times, and we talked about how we could do the reciprocal and square it, right? So here now it's like you have 2 squared times 3, which is 12. But, only if you're writing this down and keeping track of it. You cannot just change a -2. Or you can always change your fraction to a decimal. They use the decimal, and if you're using a calculator, just make sure you're inputting everything correctly. All right. So we are going to actually try it. Here, they give us the function y is equal to 3 to the exponent x, and x is equal to 5, so y is equal to 3 to the 5th power. So you can evaluate it in your calculator. This really is just taking 3 times 3 times 3 times 3 times 3. So y is equal to 243. Okay, pause the video and you work out number 6. I'll set this up for you. So let's evaluate that. Make sure you can evaluate that correctly. And I will work here. Remember, we have an a value of 3, so we have to be very careful that the only thing being raised to the power of 4 is this 4. So 4 to the power of 4. 4. So we have y is equal to 3 times this 256. And that's equal to 768. So these numbers exponentially are going to be large just based on the name. All right. Getting into graphing. All right, this gets a little complicated because these are graphs that you've never seen before probably, or maybe have just seen them, but you have not actually graphed them. So this is the first time for this. So remember what we're doing. We're graphing a function, and this is the form of this function. Okay. So what it is saying is that it's a vertical stretch or shrink by the absolute value of a, of the parent function. So what we're going to be learning about now in all of our upcoming functions is that we have this parent function. So this is kind of showing the parent function here, the blue right here. And this is only in certain circumstances when b is greater than 1, okay? When b is greater than 1, a right here is where the y-intercept is. Okay. Let's see. How do I explain this? A vertical stretch. So, when we have 2 functions and we have like the parent function, ooh, this is terrible. And then the stretch is going to like pull the function up. So when you have your parent function, okay, with a equal to 1, the parent function has a equal to 1. That's what this is, right? It's like y is equal to 1 times b to the x. That's what we're comparing it by. So what we're going to describe then is what is this effect of this factor, this constant, this a value, as it increases, what's happening? As it increases, it's going to do this, right? If it is negative, which it could be negative, then we will have this reflection. So here we have, a is positive, and our function would go like this, okay? And then here, a is negative. All right? And this is when b is greater than 1. So a has the power to make it a reflection. And it will always be like, starting out here, it will always tend to increase like that when b is greater than 1. Now, when b is a fraction, right, we've seen b be, equal to like 0.5 or 1/2 or something like that. Then you have this that looks like it's decreasing, right? It's almost like it's decreasing. So this is the graph is increasing left to right. And when it's a fraction, when b is a fraction, it is decreasing left to right. And of course, it's above 0 right here. It's on the positive side when a is positive. So, a is positive over here. And down here, a is negative, okay? And again, a is right here, the constant multiplied to the parent constant, sorry. All right. It says when a is less than 0, the graph is reflected in the x-axis. So these are things that we're going to be describing a little bit about whether it's a reflection or not. The y-intercept is always a, okay? And what we'll be learning a little bit later too is that b is that common ratio. So we're going to actually learn how to write a function. So what they're talking about here in this study tip is that it will always approach the x-axis, but it will never intersect it. So that's another common trait of these exponential functions, is that it'll never quite get to 0, okay? So let's see what this looks like. In this example, all right, we want to graph this. So we're going to make a table of values, and I suggest always using about 5 points because we need to try to get that curve in there. So then you're going to plot the points, draw the curve, but then when we describe it, it says compare, right here, compare the graph to the parent function. Now, in this case, the parent function would be y, or parent function g, I don't know what they're calling it, it doesn't matter, would be 2x, right? Because here, a is equal to 4. So since a is equal to 4, we are multiplying, or, you know, like, and it's going to be increasing, so you can definitely see that it's increasing. A is positive, so we know that this graph right here, which is the blue one, look how steep, look how fast it goes up, all right? And this g of x, the black line here, is the parent function. That's when a is equal to 1, and look how this, and they call this a stretch. So this is a vertical stretch. So when they talk about this, the parent function, they called it g of x. You could say parent function y is equal to 2x. It doesn't matter how you name the parent function, other than this part. It's a vertical stretch by a factor of 4, okay? Now, it's a vertical stretch by a factor of 4. If this, had been a fraction, it would be called a shrink. It would be getting smaller, okay? Or it would be getting, I wouldn't say smaller, but it would be out here, all right? So stretching it pulls it up. And then you compare the y-intercept, and we say that the y-intercept of, the graph of f is above the y-intercept for the graph of g. So the y-intercept of our graph is above the parent graph. And then we have to determine the domain and range. Now, look at the arrows. The arrows on your graph indicate that it doesn't matter what we put in for the value of x. The x can be all real numbers. So in most cases, unless you're going to be, limited, the domain is going to be all real numbers. But here's the important thing. What is the range? Notice that the range is greater than 0. It's not equal to 0. Remember, we talked about it will approach 0 but never be equal to it. So it is greater than 0. And that's because it is like this. If our 4 had been negative, remember that this graph would be, like a reflection of the parent graph. So then we would have y is less than 0. But in this case, we have y is greater than 0. So let's see if we can do a couple of these. This is just showing you the other one too. Now a is a fraction, right? So we notice that it's getting smaller, so it's more of a decrease. So our y values are going to decrease, and we will approach 0 but never touch it. Because of this negative a, it's got a negative 1. This red f of x, so the black one is our parent function. This is our function that we graphed from this table. And so when we describe it, we'll say that it's a reflection in the x-axis, and that the y-intercept, which is negative 1, is below the y-intercept of the parent function. The domain is, again, all real numbers, and the range is less than 0. So lots of things to keep track of. Well, let's give it a try. All right, so we want to make an XY table. All right, so XY table. So here it is. So we can, again, let's just do several. All right, and for the Y, I'm going to maybe show the work here. So what we're doing is we're taking negative 2 to the negative 2 power. So what this is doing is 2 to the negative 2 power, right? And then it's the opposite of that. So it's equal to a negative 1 over 4. Here we'll have negative 1, so this is equal to a negative 1/2. When that's 0, it's negative 1. This is negative 2, And this, when we have raised to the second power, is -4. All right, so now we want to graph these. Let's see, I'll make my axis here. I guess I should have put my work at the bottom of the page. And my y. All right. So if I'm at -2, I have -1/4. So it's like, ooh, how do you even graph that, right? -1, this is a little easier. Oh, this is the easiest, right? My y-intercept is -1. Then I have 1, -2. And then I have 2, -4. So we can start to see this curve. So all right. Oh my goodness, that's terrible, but there it is. All right. If I were to compare that to, the parent function would, kind of go up this way. Remember, the parent function, and they called it g of x last time, is just this. So it has an a value equal to 1. So a couple things that we know. We know that our red graph is, so f of x is a reflection in the x-axis of g of x. We know that the y-intercept of f is below the y-intercept of g. All right, what is our domain? The domain is all real numbers. What is our range? Our range, and the red one is ours, is less than 0, so y is less than 0. All right, let's take a look at the next one. All right, now we have, let's see, what is our parent function g of x for this one look like? It would be the 1/4 x, okay? So now our a value is 2. A value is 2. We have to make this xy table. Okay. What do I want to do? 21. 0, 1, 2, I don't know. All right. So I'll substitute in the values. So when I have -1, it's kind of like taking, remember, I'm going to take the reciprocal of this to the positive one, all right? So I took the reciprocal. So 2 times 4, so -1 and 8 is going to be an ordered pair. When it's 0, 2, and then times 1, so it'll be 2. And we already know that our y-intercept should be 2 because of the value of a right there. So that's working out very well for us. When it's 1, 2 times 1/4 to the first power, so it's going to be 1/2. And when it's 2, when this is squared, that's 16, and 2 divided by 16, holy moly, is like, is that 1/8? Looks like about 1/8. So we can change these to decimals if we want. 0.5. I don't know if this is going to help. All right. So, one thing that we know that it's decreasing. So this is why I'm giving this more on the top right up here. Right. Because we know that the graph is going to go like this. All right. And right. So, and this value of 2, it's stretching it, right? If this 2 were a fraction, it would be shrinking it. So we're going to describe it as far as a stretch. But let's graph these. So I'm going to have a 2, 4, 6, 8, 10, 12, so on. All right, so if I have -1 and 8 here, I have 0 and 2 here, and I have 1 and 5 is right there, and then 2 and... So we can kind of see... All right, so now when my parent function, so if this is 2, that's not... That's not going to be 1/2. I need to fix this problem a little bit. Yeah. So, 1/2 here, and maybe I can touch so we can bring this down. All right. Do your best. Do your best. What we do know, though, is that the parent function, in this case, and I'm changing it now, all right, would cross right here. Right, so what did this do? You know, it would be something like this. So we would have that f of x is a stretch, a vertical stretch, by a factor of 2. Okay, the y-intercept is above the y-intercept of 2 of x. All right, the domain will still be all real numbers. And what would the range be? Go ahead and pause the video and please let me know, what is the range in this function? You guessed it right, because the range is greater than 0 because the values are all above 0. Okay, the last thing we're going to do today is we are going to write the exponential function. And so let's just kind of look at this table and let it help us. 1, if it gives us an input value of 0, the output value is a. So the y-intercept is a in our function. And remember, we're doing this y is equal to a times b to the x. So a is equal to the y-intercept. It is the ordered pair when x is 0 and the output value of a. Okay. And then in this case, b, which is from the slope-intercept form, we were used to that being the y-intercept. It is no longer. Now it is our common ratio. What is this value that we are multiplying by? So this is the exponential function. So let's give it a try. All right, so make sure this is all going up by 1, and it is here. What is? It says write an exponential function. So we're going to already look for the ratio. So 3 times what is 18? 6. Then check. Is 18 times 6? Yes. And then times 6. So we have to identify A, and in this case, that's given here. It's equal to 3. B is 6. So when we have our form, we can just simply add in these values. And remember, the exponent is the x. Okay. So let's give this a try. And I'm going to go ahead and put these in the table value because this is a little crazy looking at this. But it looks like if we have, x and y, we have x as a -1.5 and y as a -4. Then from here we go to -1 and -2, then -0.5 and -1, and then 0 and -5. Now here's what's tricky about this one. Look at this. If I go from here to here, it's only an increase of half. So I want to maybe skip that, and I'm going to go from, let's see what from here to here is +1. So then I can measure this, right? And that is going to be a ratio of 1/4. So that gives me a b of equal to 1/4, right? Going from -1 to 0 is my +1, right? And here, what do I get? Half divided by 2 is my 1/4. All right, we also have visible to us our a value, and I'm going to go ahead and put that as a -1/2. Right. So y is equal to -1/2 times the value 1/4x.